In this video, we're going to look at some examples of assigning oxidation states to atoms in a compound or an ion. And our first example is sulfur hexafluoride. Before we jump into sulfur hexafluoride, let's review the rules for assigning oxidation states. Okay, so the first thing to remember about assigning oxidation states or oxidation numbers is that the oxidation states have to add up to the total charge of that species. If it's a neutral compound, then the oxidation states have to add up to be 0. If it's an ion, then the oxidation states have to add up to the charge on that ion. So free elements have an oxidation state of 0, and monatomic ions, the oxidation state is the same thing as the charge. So this is very similar to assigning the charges that we did before, particularly when we were naming compounds. And so the only thing that we're really adding here is when I have multiple nonmetals in the compound, which element takes the priority, because they may not all get to have the charge that we predict based on their position in the periodic table. So the way these oxidation rules are written, the higher the rule, the greater their priority. So there are certain metals where we always know what their charges are when they form ions. The alkali metals, the alkaline earth metals, aluminum, zinc, and silver are +3, +2, and +1. The other rules down here are the same that we predict based on their position in the periodic table. Again, the only thing that we're adding is the priority. So fluorine comes first. Fluorine, compared to all other nonmetals, will get to have its -1 charge. Hydrogen gets to be number +1 unless fluorine outranks it in that particular compound, and so on. Oxygen, we know, likes to be -2, but it takes a backseat to fluorine and hydrogen if there is an incompatibility. So if we go back to sulfur hexafluoride, so I see that sulfur generally likes to be -2, but fluorine is above it, right? And so if fluorine and sulfur got to have the charges that they would both like, this compound would have 6 fluorine, so that would be -6, plus a -2 for the sulfur. This compound would have a -8 charge. And obviously, that's not the case. I didn't write any charge up here, so I know that that compound must be neutral. So the way this works is, because fluorine is higher priority, it gets to be -1, and then the sulfur has to accept whatever oxidation state it needs to in order for the compound to be neutral in this case. So I'll do this the same way that I determine the charges on metals, like transition metals, when I'm naming them. And so I'll write a little formula, right? Sulfur is my unknown. That's what I'm solving for. The fluorine I know, there's 6 fluorines, and they have a -1 charge. And then those have to add up to be whatever the charge on the species is. In this case, there's nothing in the upper right-hand corner, so I know that it's neutral. So the charges have to add up to be 0. So the sulfur that I'm solving for, 6 times -1 is -6. So I've got sulfur -6 has to add up to be 0. So now I'll add 6 to both sides, and sulfur is 6. So let's go to the next slide. And I'll just write my answers here. So the oxidation state on sulfur that we determined on the previous slide, sulfur is +6, and the fluorine is -1. All right, let's look at another example. All right, so now we have the nitrate ion, NO3-. So let's go back to our solubility rules. All right, so I have nitrate, NO3-. So I see that the nitrogen group, as we know from its position on the periodic table, nitrogen likes to be -1, oxygen likes to be -2, but if everybody got to be what they wanted, in this case, the 3 oxygens would make -6, plus the -3 from the nitrogen would be -9, right? Obviously, nitrate does not have a -9 charge, it has a -1 charge. So because oxygen has a higher priority, it gets to be -2, and then the nitrogen has to be whatever it needs to be in order to give the compound, or an ion in this case, a -1 charge. So let's write that out on the next slide. Okay, so nitrogen is what we're trying to figure out. I know that I have 3 oxygens. I know that those oxygens are each -2. And I know in this case, because the ion has a -1 charge, the oxidation states have to add up to be -1. So the right-hand side of my little equation here is -1. So the nitrogen that I'm solving for, I've got 3 times -2 is -6. All right, so now I'll add 6 to both sides. So -1 plus 6 is +5. So the oxidation states, oxygen has a -2 oxidation state, and the nitrogen has a +5 oxidation state. All right, let's do one more example. Okay, so here I have an ionic compound, and now I've got 3 things. So it might be even harder. But remember, oxidation states for monatomic ions are the same thing as their charges. So when I see that I have an ionic compound between chromium and phosphate, I'd figure out the chromium just as I would if I was trying to name this compound. And so I know that phosphate, the whole thing, the PO4 together is -3, so that means the chromium must be +3. So I already know that chromium has an oxidation state of +3. So now I just need to figure out what is the oxidation state on the phosphorus and the oxygen in the phosphate ion. So I know phosphate is PO43-. So whatever the oxidation states on phosphorus and oxygen are, they have to add up to be -3. So let's go back to our rules for assigning oxidation states. All right, so we're trying to figure out what are the oxidation states on phosphorus and oxygen in phosphate. So phosphorus is in the nitrogen group, so it would like to be -3, but oxygen has higher priority. Again, if everybody got to be what they wanted, this thing would have a charge of -11. Obviously, it's -3, so oxygen having a greater priority than the nitrogen group where phosphorus is, oxygen gets to be -2, phosphorus has to be whatever it needs to be in order to give the ion a -3 charge. Okay, so again, we're trying to figure out phosphate. So phosphorus is what we don't know. We're trying to figure that out. I've got 4 oxygens. They're each -2. And now they have to add up to be -3, because that's the charge on the ion. So phosphorus -8 is equal to -3. So I'll add 8 to both sides. -3 plus 8, the phosphorus comes out to be 5. So my oxidation states, chromium, we already figured out, is +3. Oxygen gets to be the -2 that it wants, and phosphorus must be +5.